Hi, my name is Professor James. Welcome to this journey through space. Today, we are going to study the chapter, which is Simulation-Based Testing and Digital Twins. In this chapter, we'll explore digital twins, virtual replicas of physical aerospace systems, and how they are transforming aerospace engineering through real-time data integration and advanced simulations. Simulation-based testing uses virtual environments to test aircraft systems under extreme conditions, eliminating physical risks and reducing development costs. Let's explore how digital twins and simulation-based testing work together to optimize aircraft performance, maintenance, and design. What is a digital twin? A digital twin is a virtual representation of a physical object or system that evolves over its life cycle using simulation, machine learning, and real-time data integration. Dr. Michael Greaves, who first conceptualized digital twins, defines them as a digital replica of a living or non-living physical entity. In aerospace, digital twins are used to create accurate virtual models of aircraft, engines, and components that evolve with their physical counterparts using sensor data. These virtual models simulate real-time operations, providing insights into the current and future performance of the system. Digital twins help engineers predict system behavior, optimize design, and perform predictive maintenance, reducing the risk of failure and extending component life. The core idea is to create a feedback loop where real-time sensor data constantly updates the virtual model, making it a living digital replica of its physical counterpart. Digital twin architecture. The architecture of a digital twin involves several key components that integrate physical assets, sensors, and simulation models. Physical assets. This includes the actual aircraft, engine, or component being modeled, such as wings, propulsion systems, and control surfaces. Sensor network, a network of temperature, pressure, vibration sensors, and strain gauges, collects real-time data during operation, such as engine performance or structural integrity. Simulation models. These are the mathematical models representing aerodynamics, structures, thermal, and propulsion systems, and other key engineering disciplines. Digital thread. A continuous data flow connects all elements: design, manufacturing data, operational history, and maintenance records, allowing seamless updates to the digital twin. This architecture ensures that the digital twin evolves over time, improving its accuracy with every real-world data update, creating a complete simulation environment. Real-time sensors and feedback loops. The backbone of a digital twin's functionality is its ability to receive real-time data through a variety of sensors and feedback mechanisms. Sensor types used in aerospace include accelerometers, gyroscopes, strain gauges, and temperature-pressure sensors. These sensors collect data during flight, such as vibrations and fuel consumption. Feedback loops allow data to flow bidirectionally between the physical aircraft and its digital counterpart. The data updates the virtual model, enabling real-time simulations and performance predictions. By continuously updating the model, engineers can gain insights into component performance, such as early signs of wear or potential failure. Feedback loops also enable optimization. Simulations can be updated dynamically based on real-world data, improving performance over time. These loops ensure that the digital twin always reflects the current state of the physical asset, enhancing predictive maintenance and optimizing operations. Flight simulation and virtual testing. Flight simulation and virtual testing are crucial applications of digital twins in aerospace design and validation. Flight dynamics modeling uses CFD and FEA to simulate aircraft behavior under different flight conditions, like maneuvers, wind gusts, or turbulence. Hardware-in-the-loop simulations integrate actual aircraft components, like control systems, with virtual models to test their response to simulated conditions. This allows engineers to test hardware in a virtual environment before physical testing. Virtual flight testing enables the testing of extreme scenarios, e.g., high-speed stalls or structural failure, without physical risk, improving safety and reducing testing costs. Virtual tests can also simulate edge cases, like unusual flight paths or emergency landings, allowing engineers to identify design flaws before they occur. These virtual environments help engineers conduct comprehensive testing and analysis, accelerating the design process while minimizing physical prototyping costs. Connecting sensors to CAD models. Connecting real-time sensor data to CAD models through digital twins allows for real-time performance analysis and design refinement. IoT gateways enable the collection and transmission of data from aircraft sensors to simulation models, providing real-time updates. The use of Simulink helps process and analyze the data, feeding it back into the CAD models for visualization and real-time simulation updates. This creates a closed-loop system where sensor data is continuously used to update the digital twin, simulating the behavior of the aircraft throughout its life cycle. Engineers can use these updates to predict future behaviors and make adjustments to designs or maintenance schedules. This integration of IoT, Simulink, and CAD models streamlines the design-to-production cycle, improving both accuracy and efficiency in aerospace engineering. Sensor data processing workflow. The processing of sensor data is a multi-step workflow that ensures accurate updates to the digital twin. Data acquisition begins with physical sensors collecting measurements from the aircraft during operation, such as strain, temperature, and vibration data. Signal processing involves filtering the raw data to remove noise and calibrating it to account for sensor inaccuracies or environmental factors. Data integration then combines this processed sensor data with existing simulation models and historical data, creating a comprehensive virtual replica of the aircraft. The model is updated with this new information, ensuring that the digital twin always reflects the real-time operational state of the physical asset. Finally, simulation execution uses these updated models to predict future states, such as wear and tear or operational efficiency, and provide insights into maintenance needs or performance optimizations. Predictive maintenance. Using simulation. One of the most significant applications of digital twins is in predictive maintenance, which allows for proactive identification of potential failures. Continuous monitoring of aircraft components, such as engines or landing gear, enables the early detection of performance issues before they lead to failure. By comparing real-time performance data with simulated behavior, engineers can identify anomalies and predict when maintenance is needed. Using simulation, digital twins predict remaining useful life, RUL, for individual components based on current operating conditions and historical data. This enables optimized maintenance scheduling, ensuring that components are replaced only when necessary, reducing downtime and maintenance costs. Predictive maintenance can reduce aircraft downtime by 30% and maintenance costs by 25%, leading to more efficient operations and fewer unplanned service disruptions. Digital twin maintenance workflow. The digital twin maintenance workflow involves continuous data collection, real-time updates to the virtual model, and optimized maintenance planning. Data collection is ongoing, with sensors monitoring aircraft health and transmitting real-time data about critical components. Digital twin updates involve recalibrating the virtual model based on new sensor data, ensuring it accurately represents the aircraft's current state. Condition analysis compares the virtual model's performance to baseline models to detect any discrepancies or signs of wear. Maintenance planning uses these insights to optimize the scheduling of maintenance based on predicted component life and operational conditions. This workflow ensures that maintenance is targeted and efficient, reducing unnecessary inspections and minimizing the risk of in-service failures.